So just when your region of interest in the left region, then you can just calculate the E field that is caused by this one and the electric field caused by this one, and then you just add them together. Right. You can also see this kind of method through the way that they ask the questions. So in this case, it is very straightforward. If you want to calculate the electric field at the left region, that is the point 1, right? So then you need to, first of all, before you do all of this, you can calculate the electric field that is caused by sheet A and sheet B. Any problem with this? Any problem? Okay. So
揉出射，是差值，但是这个是满倍的，因为这边是 plus， 这边是 minus。剩下那两个是零的。这个 plus 加这个 minus 这边的零，这个 plus 加这个 plus 等于零，这个 minus minus 等于这个等于满倍的。
So I remember I mentioned to you when I do the electric field that the electric field can be calculated by the Gauss's law. You apply the Gauss's law. It's actually the charge over the epsilon. Do I need to repeat? No need. Okay. So for example, for sheet A right now, this is sheet A. This is sheet B. For sheet A right now, so the electric field that is caused by okay. So for sheet A right now, we don't have this part. Okay. It has two regions right now. First is left. Another region is right. So I just write E A. I write this like the electric field caused by the sheet A in the region of P1. Okay. This one I write it. First is this is a vector. Vector has a direction, has a magnitude. The direction is because this one is a positive charge and this one is negative charge. So this one, the electric field is in this way. And this is Z. This is Z. So the direction is minus Z. Okay, I write it over here. And then I write the magnitude. Magnitude is actually the Q over epsilon. The Q of this sheet is rho. And wait. Over 2 epsilon. Epsilon. Yeah, we already have that. See, we have a previous example that we write. Yeah. This one is rho over 2 epsilon. We talked through this last session, right? So this one is rho over 2 epsilon naught. This is for this one. Okay. So there's another one that is the electric field caused by point A in region 2 or 3. Positive Z direction, and then rho over 2 epsilon. So same things can be written for B. Do I need to write it?
它如果是一个作用的话，它就是有一半是导，有一半是两个媒介，一个媒介是导体，没有那个一个作用，对吧？
That is the electric field. So in region 1, we can just add this one and this one. In region 1. Okay? So this one add this one, that is 0. So in this case, the electric field is 0. It is P2. P2 is this one and this one. So that is 0 over this. Okay, don't forget the direction. And P3 is this one and this one, that is 0 again. So again, just a very kind reminder of you. This one has a 2. Oh, I forgot that 2. So I said, when you remember the conclusion that get from the lecture notes, be sure you remember it correctly, or else you get the wrong answers. Okay.
对，不是，
About the assignment, do you have questions?
Last question.
Okay, let's see. Last question you ask. And I give some hint, right? About this one. Yes. So. Let's see, what is find the capacitance for a conducting sphere with radius A. The conducting sphere, so it has all the positive charges resides on the surface of this one, right? So it is all positive charges, and it has a radius of A, and the total charge is Q. And the epsilon naught. Okay. So. Like when we want to calculate the capacitance, we need to know the basic formulas, right? For the capacitance, it is a Q over V, right? The Q here is a known parameters, and here we need to get the V. So what is the physics meaning for V?
Potential.
It's potentials. It is potentials. So we want to know the potentials over here. And how do we calculate potentials? So potentials is actually like this. Something like this.
Minus.
It's a minus sign. Electric potentials. Yeah, it has minus plus 1 to so it is like this. So we need to know C, and then we need to know V. We want to calculate V, we need to know E here. So how to calculate the electric field? The electric field, first of all, this is a conducting sphere. There's no charges inside this conducting sphere. So the E field inside this one is 0. So when your R is smaller than A, that is electric field is 0. Okay? So right now our region of interest is R that is larger than A, right, for this kind of region. So for potential at P. Oh, by the way, the P over here is actually a point. The P over here means a point. That is a point on this Gaussian surface. Okay, and the P point has a radius of R. So let's see. we used to have an equation to connect the D and E. So it is this one, right? Can you see? This is connection between. This is how we calculate the E based on the D. How we calculate electric field E based on the electric flux. Okay? Do I need to repeat again? Because we go through this many times. You guys, does this ring a bell to you? Like this. This is Gauss's law. Yes, this is Gauss's law. So this is divergence of D equals to rho, right? So this one is actually the third equation of Maxwell's equations. This is I'm not going to repeat this one. And then this is how we integrate. So we integrate both part over a volume of V. So over a volume of V, because this one is rho V, so that is the charge density over a volume. So we integrate this charge density over a volume, then we can get the total charge that is inside this volume, that is Q, capital Q. And then we also know that this is the third one is divergence theorem, right? Divergence theorem. So divergence theorem is it's a relationship between a volume and the surface. Right? It is between the volume and the surface of that volume. This is divergence theorem, right? So after we know we know this. So this one equals to this one, and this one equals to this one. So these two are the same thing. So that is how we get the integral form of the Gauss's law. That is this part. That is the electric flux dot the area that it will go through. Then you can get the total charge. What does that mean? Okay, just the physical meaning, right? Here, now this is a point charge. Okay, now it has electric field that is pointing outward, and then you have a charge, and this is the electric field that is pointing outward. As long as you have the E, also you have the D, right? They're basically pretty much the same thing, because D equals to epsilon E. This is the constitutive relationships. Okay, so right now, right here we have this one that is a closed surface, D dot ds equals to Q. That is the total charge. Then in this case, I just close this everything with a surface, and then I call it Gaussian surface. And then the surface is S. Right? So then then I can just use this one to calculate the D. Because the Q here is just a point charge. Maybe it is with positive Q. So I just substitute this with Q. And then over the closed surface. Right? The closed surface over here is just 4 pi r squared. Right? So 4 pi r squared, and this one is r. So anyway, this one is very important because it helps us to calculate the electric field based on a charge. Right? The reason why I mentioned this is because it is very useful when you calculate about capacitance. The capacitance, you need to know the C, and the C is based on the potential, and the potential is actually based on the electric field. The electric field, how can I calculate electric field? Electric field is basically use the constitutive relationships. Okay, so it is minus this part, that is D over epsilon dl. Right? Because this one we know, and right now it's just a problem to solve D. And I also can tell you that the D can be calculated based on this relationship. That is to say, the D can be calculated as long as you know the charge and the length. So then for this case, right now, for this case, we have a closed Gaussian surface, and P is a point on this Gaussian surface with radius of r. Right? So then we are interested to know at this point what is D. Okay? At this point, what is D? At this point. Like at this point the D is, just assume it is D, alright? And then what is ds? So it is a closed surface. I'm sorry, this one. It doesn't have the integration. This one is a closed surface that I can enclose everything. So for this case, the area of the enclosed surface is 4 pi r squared. Okay? And this is the left hand side. Right hand side is the Q total. That is a very known number. That is Q. And this one, I substitute epsilon E 4 pi r squared and Q. So this is how we calculate the electric field. Okay. And the epsilon, of course, in this case, that is epsilon naught. So that is how we calculate the electric field that is caused by the charges residing on this conducting sphere. And yeah. Okay. So now we know the E. After we know the E, then we can know the potential. So the potential right now, our region of interest again, our region of interest is R larger than A. It is outside the conducting sphere. So how can we calculate the V? Then in this case, that is this is. Oh, by the way, you guys know why there's infinity? Right? So the electric potential is actually has a reference. The reference we just default to set this reference to be at infinity. Okay? And what is the meaning of voltage? Voltage is the difference between the electric potential. So at any point it has an electric potential, and the reference is set to infinity. And this is V1, and I have another point that is V2, has an electric potential of V2, and the reference I set is also infinity. And I use V1 minus V2, I can get the voltage between them. So that is V12. So voltage is actually a relative term between two things. But electric potential is like an absolute term with the reference that is set to the infinity. That is the reason why here is the infinity here. Okay? So I put infinity here. And right now the E has an expression over here, so the variable is R. Right? And then the R has the range of this is the range. Right now our region of interest is larger than A, so our region of interest is any area that is outside the conducting sphere until it is to the infinite far field. So then the radius is between this point to the infinitely far. So this is the radius of A, and this is the radius of infinity. So this is an infinity, and this one is oh, sorry. I can't write it here.
Yes, sir. Should be 1 on E.
A and R. You didn't mean R is equal to infinity.
any point.
Yeah.
Okay. That is any point. So any point has a radius of r.
Yes.
Okay. So then E I just substitute.
We need R minus A.
Yes. R minus A. The below one is should be A. Plus
No, we don't need r minus a.
Why?
Why there's r minus a?
Because A is the
I know.
medium of
I mean, the region of interest is in this region, but the r, this r is 0. This is the r.
Okay.
Okay. So your r has the range from a to infinity.
R range from A.
You can't write a minus r minus a. R minus a is just this length. What does this mean?
But we have to find the voltage between point A and point R.
No.
Then how about V12 and this one?
So I said this one is absolute value that is compared to the infinity.
Okay. So this one is absolute value compared to infinity.
Yeah.
So it's not compared to A.
No.
Okay.
So yeah. So this one is Q over R square. And this one is